Alrighty. Let's see if I can find my notes. All right, we were right here on acid rain. So when we hear about acid rain, that doesn't mean actually that it's raining acid. But what happens is the water will come down and mix with some of the industrial gases that are produced, and then that will form an acid. So industrial process produces gases like nitrogen monoxide or nitrogen dioxide, carbon dioxide, sulfur dioxide, sulfur trioxide. So when the water comes down, then the water will combine with that and then produce acids like sulfuric acid or carbonic acid. And then that's what we're talking about when we say it has acid rain. And then those can be really damaging, especially to older buildings that are made out of marble or statues that are made out of calcium carbonate. Like if you know the old statues that look like they're kind of rough, it can really damage those. So today we're going to be talking about acid-base titrations, and during those, a neutralization reaction happens. So we're just going to mention that a little bit, although we have talked about them some already. So neutralization is the reaction of an acid with a base to produce water and a salt. And remember, salt doesn't just mean that it has to be sodium chloride like table salt. Salt is any ionic compound made out of a positive cation and a negative anion. So we'll see those with acid-base titrations. We're going to skip that bottom part because that's net ionic, and we've already done that. We did that already separately. So if you'll move on to where it says titrations, I think maybe back of the next page. And we're specifically looking at acid, oops, I don't know what that is, base titrations. And we're doing strong acid, strong base. So because there are other types of titrations that don't have to be acid and base. And then if you were doing like a weak acid and a strong base, it kind of gets a little bit harder to figure out the things that we're going to look at today. Caught up here on my notes. So a titration is a neutralization reaction of an acid by a base or vice versa. And then you're usually doing it to find the concentration or the in molarity of your unknown acid or your unknown base. And you would know the concentration of the other one. So if I was trying to find the acid, you'll need to underline this. If I was trying to find the acid, if that was my unknown, then that means I would have to know the molarity of the base. You can't not know the molarity of both of them. So the titrant or titrant is a solution of known concentration, and it's in the burette. This is a burette, and they're used for titrations. You can see they have a lot of demarcations on them, so they're a little bit more accurate than even a graduated cylinder. And the numbers actually start smaller and get larger. So whenever you're trying to figure out how much of your titrant you've used, you're not always starting at 0. Sometimes you might be starting somewhere else. So to find out how much is used, you would take your final and subtract where you initially started, and that would give you how much of your titrant you used. And you'll see her do that in the video. She won't fill it all the way up to top, all the way to the 0. She fills it up about, I don't know, 3/4 full, and then she jots down that number. Because if you don't start exactly at 0, which you don't have to, then you need to know your beginning number. And then that's what you'll be using tomorrow whenever you do those in Gizmo also. So that's the titrant is added to the solution of the unknown concentration until that substance being analyzed is just consumed. And the analyte is going to be the solution that is unknown. I feel like I spelled that wrong. I'll check into that. You'll probably never have to spell it, so it looks weird, doesn't it? Yeah, I think I can't really figure out what I left off, but I'll look at it in a minute.
I think it's just because the K looks like an X.
Because the K? Oh, no, I feel. So I feel like that's spelled wrong. But anyway, I'll Google it in a minute. Now I can't even remember what I was trying to say about the analyte. So you'll see the analyte's like it underneath in a Erlenmeyer flask, and so that's going to be the thing you do not know. You know how much of it you have, but you don't know its concentration, and that's also where you would put the indicator. Remember, an indicator that we're using because we're worried about acids and bases are going to change color whenever the pH changes. So the end point is when you see that change in color at the ending of the titration. When it changes color, then that tells you to stop. Phenolphthalein is really common. It's clear, and then it will turn pink. You're using, I think they give you 3 to choose from. Yes, tomorrow I think methyl orange will go from orange then like to a navy blue, but they change that color whenever that hits a certain pH, and then that tells you that you need to stop the reaction, and that's because you have hit what is called the equivalence point. So the equivalence point is a point at which the 2 solutions used in the titration are presently in a chemically equivalent amount. So for our acid base, that means when I hit the end point and I see a color change, the moles of my acid are equal to the moles of my base. That's supposed to be an A. So the end point is the color change, but the end point tells you you're at the equivalent point. And we're sticking to a strong acid, strong bases. And we know that if we wrote that as a net ionic, it would just really end up being the ions coming together to form water. So for a strong acid, strong base titration, when you get to the equivalent point and you stop titrating, your pH should be pretty close to 7. Now, if I did like a strong base with a weak acid, that equivalence point, whenever you got to that, it still would be in the base area. So only time if you got strong is that when you're going to have your pH actually at about like 7. So the formula we're going to be using for this is MaVaNA is equal to MbVbNb. So it looks like our dilution formula that we've already used, and then it's a couple of N's tacked on. So M is molarity, big M. V is volume. It can be milliliters or liters, but it has to be consistent. Na for your acid is the number of acidic hydrogen. So that means the number of hydrogen that are there at the beginning of the formula. And so Nb for the base would be the number of hydroxides. And it's only the number of hydrogen or hydroxides in the formula. It does not include the coefficient. It does not include the coefficient. Yeah, we can put a plus there. Although you won't see it as an ion because whenever you count them up, they're still part of the formula. But yeah, an acidic hydrogen really is the plus with the ion. So for example, if I had hydrochloric acid, that N would just be equal to 1. But if I had sulfuric acid, that N would be equal to 2 because I have 2 of them. Where here on the hydrochloric, I just have 1. And it's the same thing for our bases, but instead of hydrogen, we're looking at hydroxides. And it doesn't matter. I could have a 14 in front of this that I need it to balance it. It still would just be N equals 2 because the coefficient is not part of figuring up how many hydrogen you have. It's just within the formula itself. All right, so let's look at a couple of problems. They're pretty easy. All right, so here we got our first one. So third period, I was really trying to balance this equation. And I had a lot of trouble balancing it. Can anybody tell me why I had trouble balancing it? Because there's magnesium over here, right, but not over there. So that's not a good equation. That could be why I couldn't balance it. So it should have been hydrochloric acid plus magnesium hydroxide gives me water plus magnesium chloride. And then if you actually write it correctly, it makes it a lot easier. Put a 2 there for my chloride, which now up my water to 2. So that's the neutralization reaction for that acid and that base. And you're going to need to write one of those on the quiz on Friday based off of the description. So you're going to have to write some formulas for some acids on Friday. So I know y'all don't, everybody likes to avoid the acids for some reason. And in the end, it really doesn't become important what the equation is, because when I'm going to look at here, I'm only looking at the actual formula. I'm not looking at the coefficient. But anyway, you do have to write at least one neutralization reaction. All right. It says, suppose you know that you have 20 mils of a 0.0050 molar magnesium hydroxide. So that's all my base information. And that's what is required to reach the equivalence point in the titration of 10 mils of an unknown molarity of hydrochloric acid. So there's my acid information. So that means that I had my magnesium hydroxide in here. I carried out the titration, and it took 20 mils for me to see the color change. And in the Erlenmeyer flask, I knew it was hydrochloric acid. I don't know its strength, and I knew that I put 10 mils in there. So what I need to figure out is my MA. So we'll just start our formula, MA, and then times VA, which here it says you use 10 mils. And then my Na for my acid, which is hydrochloric acid. So what would my N be? Just 1, right? Because I just got that 1 hydrogen. And then I do everything on my other side, except I happen to know more about my base. So 0.0050 molar. And it said it took 20 mils. And what would be the N for my base? Remember, now I'm looking at hydroxides. 2, exactly, perfect, because I have that subscript. So at this point, we just do a little bit of algebra. I feel like we've been doing similar problems to this a lot this second semester. 2 sig figs. I think there are several things in there. If not everything, is 2 sig figs. So what did y'all get? And you get just 0.02 on your calculator, and then you kind of stick that other 0 in there for sig figs. And my units are M. Remember, even if you put MA equals, you still have to put the unit on there because the unit goes behind the number. Not too bad. It's real similar to that dilutions that we did. So probably the worst part of it will be writing the acid name. All my classes, every class hates to write names for acids. All right, so let's see what we got going on this titration. In this titration, 27.4 mils of my barium hydroxide. So that's once again, that's my titrant because I know its strength. And to do the titration, it took 27.4 mils. And then I have my acid, hydrochloric acid. And I start it with 20 mils. That's how much I put in my Erlenmeyer flask. And so once again, my MA is my unknown. So I'm just going to start plugging everything in. MA, BA. So right here it says I use 20 mils of hydrochloric acid. And hydrochloric acid, what would be my N? Just one, right? Because HCl, I just have one hydrogen. And then on this side for my base, I knew the strength already. 4 molar. And I used 27.4 mLs. And then for my barium hydroxide, what would have been my N? 2. So once again, a little bit of algebra. I think we can have, how many sig figs on this one? 3, exactly. So we can have 3 sig figs on this one. What did y'all get for that one? 422. All righty, that would be what you got. All right, why don't y'all try the next one? Try the next one. Would somebody have an answer for that one? I didn't get that. What did you get? 0.0786. And I can tell you one thing that might have messed you up. Sulfuric acid is H2SO4. So if you forgot to put that 2 there and said your Na was only equal to 1, that would have messed you up. That's probably the most common way that people got mixed up on that one, because you had to actually write the formula. So before Friday, go over your rules again on writing formulas for those. All right, so the last thing that I want to end with in our notes is like a little, trying to draw a little drawing. So once again, just kind of talking about real titrations and using our burette. So let's say that's supposed to be a burette. Okay. And like I said, it has a 0 up here somewhere, but like it's very hard when you're filling something to get exactly on the 0, and there's no need to. So let's say that I filled it up and I filled it up just to here. So that was my starting point. And when I read that, that was 5.25 mLs. And then I titrated, I was doing a titration, and whenever I finished, I was down to here. So this is at the end, and that is 20.25 mLs. So if you needed the volume in there, the volume would not be 20.25, would it? You'd have to take your, 20.25 and subtract where it started from. And then that difference is how much of whatever that solution was in there that you actually used. And so that's kind of what I was trying to say earlier when I was trying to explain that. And the reason I bring it up, because you'll come across some, I think, on the practice, and then I know one in the quizzes, you have to, on the quiz, you have to do that for one of them. But you'll see also on the video tonight as you watch this, if we were doing a real titration, we would we wouldn't wash this out with water. You wash it with actually the solution that you're using. So let's say that I'm putting potassium hydroxide in here. You need to rinse it with the potassium hydroxide at least 3 times before you do a real titration. Because if you did water and then you had some water bubbles, that would take up some of the volume and it would give you a bad reading. And this one's real that it got open. So it'll open and stuff would fall through there. So you wouldn't even want to open that up when you were cleaning it. The other thing is when you fill it, sometimes you end up with bubbles down in this tip. And before you started your titration, you would open it up and put it in like a waste beaker until you could get all of the bubbles out, and then you would close it out. Because if you didn't do those things, then the bubbles take up volume, and then that messes up your reading. So you'll kind of see those things when you watch your video tonight also. All right, y'all might have a minute or so to, get a minute or so to try a problem, I guess. And like I said, we will quiz on this on Friday.